The plan for today is to take any questions on the bell curve, normal distribution, make sure that makes sense, and begin and probably not end the last little bit, which is called the central limit theorem. We're going to do an experiment today with some dice. I doubt we'll actually finish the experiment all the way to the end. Just based on history, it takes more than one class period to kind of properly isolate what's going on. So we'll just carry it over into Thursday, and then call it a day then. So just go on again. Go on. Hey David.
Hey John.
What you need, man? Hey, not a problem.
You got an extra projector there?
Oh, you know what?
Can I borrow it? Yeah, let's check it out.
Oh, hell yeah, we do. I don't know why that's working. It wasn't working before.
Yeah.
I think I stole it from you before.
One time I got two. This time you got two. We're even.
So anyway, first things first. Any questions on normal distribution? Apologies, I didn't get a chance to make videos for this yet. I want to make videos for the last few sections tomorrow after office hours. Fingers crossed. My goal was to do them yesterday during office hours, and then after office hours, but that time afterwards just evaporated. So hopefully tomorrow after office hours, everything goes well. So, any questions on normal distribution? Bell curves. Slap this up here. There's that. So hopefully we'll have. I haven't gotten a chance to look at this yet to see which ones of these have solutions. Whatever ones don't, I'll make videos for. Did anything in there give you grief? Give you agita, Bishop, California, shower head 68 inches? Upset anybody?
Can you go over that one?
Sure! What gave you grief, Skylar? Which one in particular? Or just E1?
Just E1.
E1, for sure, for sure. So the gist is here, we'll go to Bishop every once in a while, my family and I. Great climbing down there, fantastic rock climbing. And beautiful area, it's kind of like Bend, high desert. Not the Cascades, it's the Sierra Nevada, thank you Andrew. Yeah, Sierra Nevada right there on the western part of the town, absolutely gorgeous. But we decided to splurge this one trip and get a hotel. So we got a Ramada room, which is splurging for rock climber bums. And I went to take a shower, then I stepped in the shower and the shower head was like right here. And I thought, well, that's interesting. So I measured it, 68 inches from the ground to the top of the shower head. And I thought, well, that's mindfully inconvenient for a 5'11" dude. So I decided to see, okay, so what percent of the population are these people upsetting by having a shower head at 68 inches? And so I did some Googling, and I got the average height of a guy is 70 inches, American, full-grown American male, 70 inches, plus or minus 3 inches. This is all based off of U.S. Department of Health and Human Services. So my question is, what percentage of men can fit comfortably under the shower head? This is great. Now I did create a definition of comfort in this. Comfort means you have to have at least 2 inches between your top of your head and the shower. This was fun for me. I mean, 68 inches, I turned the thing up like this and had like a little waterfall going into my eyes, which was nice. It was fun. But comfort, we'll design it as having it high enough so you got at least 2 inches between the top of your head and the shower head. Okay? So, first of all, how do you know, besides the fact that it's in the section called normal distribution, if you were to encounter a problem like this, and you're going to encounter a similar problem on your out of class if you haven't taken a look at it yet. If you have taken a look at it, you're going to see a very similar problem to this on your out of class that involves airline seats. So how do you know that these problems are normally distributed? And it's almost a trick question.
Because you're either comfortable or not.
That would make it by no means, wouldn't it? That's good. I hadn't thought about that. Yes, but that you can view this, Michael, in that way that you're either comfortable or you're not, depending on what side of the curve you fall on. Good. But the problem with this is that isn't. In order to measure that, we have to look at the heights of the people, and that becomes a continuous measure, which we can't count. We have to measure it. Thank you. That's very good, though. Don't think too hard. Read the problem again.
Is it because there's a standard deviation?
Well, that's a good indicator. Yes, I won't give you things like a mean and a standard deviation for a binomial because you can calculate them very easily with the technology I've given you. I'll tell you in the problem. I have to because I can give you a mean and a standard deviation for anything. Heck, for any data set has an average, and any data set has a plus or minus around that average. But not every data set is shaped like a bell. But heights are. Heights, weights, things like that. The headlight lifespans sometimes are. So these definitely are. If you put people onto a graph and you stack them up, most of them are near the middle and then they tail off on the ends. Somebody just showed me a t-shirt. There's a website called thinkgeek.com and they showed me a cute t-shirt. It's a picture of a bell curve. and it's got 1 standard deviation marked and 2 standard deviation marked, and it's got an arrow pointing to outside the 2nd standard deviation that says you are here. And I just love it. It's the low one. And I just love that. One of my students actually got the joke. Yes! We get it. We get the idea of an outlier and a bell curve. So, we know it's normally distributed. What kind of a problem is it? Is it forwards or is it backwards? Why is it forwards, Jamie? I agree wholeheartedly. Why is it forwards?
Because you're trying to find the percentage.
Perfect, my friend. We're trying to find the percentage of those that fit under the shower head. So you know how tall you can be to be comfortable, but you don't know what percentage can fit. That makes it a forwards problem. If you're looking for a percentage. Beautiful. So there's a kind of a set of steps for the forwards problem. First of all, identifying as forwards is huge. Once you know it's forwards, you can't go straight to your program, can you? Why can't you go straight to the program once you know it's forwards? There's a bit of a problem.
Because it's very standard.
Good, Jamie, thank you. Perfectly said, perfectly said. When you have a forwards problem, your program needs this kind of a setup. Your program needs this. This is what that t-shirt had on it, and then it had a little dot right here. You are here. Cute, cute. So that's what your program needs. But what you were just given is not that. You were just given, what number is in the middle?
7.
Yes, for guys it's 70 inches. And what's the plus or minus? 3. So this goes up to 73, 76, 67 down to here, 64 down to here. So that's the problem with that. So we live on this, and we have to get over to here. And that's okay. Where are we on this? I mean, this is a lot of numbers, yes? Where are we on that? And this is, I think the trickiest part of the problem is identifying. I made up something here. I created a definition of comfortable. I said to be comfortable, you have to have what? At least 2 inches between the top of your head and that shower head. Which means, to be comfortable, how tall can you be maximally? 66 inches, because the shower head is at 68. It's here, which means you can't be any taller than 66 in order to be comfortable under it. By my definition of comfort. Now I made that up, of course.
So 1/3 over the negative.
Good! Exactly, Kate, and that's what we have to find right there, her 1/3 over. Good, very nice, my friend. So I'm going to do it in 2 parts if it's okay. Kate's just discovered what we need to enter into the calculator. If you don't see it, that's okay. This is why we do it in steps. So here is the point we need to be no taller than.
-4/3.
Good, very nice. But you said 1/3 over from the standard deviation, which is correct. So basically, 66 inches is the cutoff. Anybody over 66 inches is not going to fit comfortably. They're going to be too close to the shower head, or in my case, above it. Anybody below 66 is going to be just fine. So here we go. We go right there. That's what we need to find. That's what we've got to find right there. Let's make sure that makes sense before we go any further. Let's make sure that makes sense before we go any further. Can you think of a corollary problem on, this has been about a week now, you might not remember it, on Tuesday that we did that was similar to this? We did pregnancy and we did IQ. Do you remember any of those problems were kind of resembling this?
Pregnancy with the newborns, or the preemies?
That was a backwards problem, but yes, it looked like this one, didn't it? Yes, it was going to the left. I was actually going the other way with the induced, because that was a forwards problem. It was going to the right, which makes it look different. I was thinking more forward, but yeah, the
I
previous...
thought you meant literally one.
No, that's perfect. That's perfect. So you can remember the curve going to the left, the lowest 5%. Good. Okay, now that's fantastic. We now know that's the area that we need to approximate. But we can't put 66 into our account. We know it's a forwards problem, yes. We know it's a left shade. Is everybody okay with why I'm shading left? I mean, if you have to envision a shower head, you can be as low as you want, but if you get too high, then you're not comfortable by my definition of comfort. So all we got to do is do the conversion and figure out where that bad boy lives on this scale up here. That's all we're going to have to do. Now, I will have the formulas for conversion on the board for you during the exam next week, and you'll have access to them, of course, on your out-of-class exam. But for the forwards conversion, and this is what Kate did in her head back there, which was awesome. For a forwards conversion, if you have a raw score X, which we have, 66, you're going to dump the average and divide by the standard deviation, and that's going to convert that X into a Z. That's going to do the conversion and get you off of that scale and get you onto the scale that I built your program around. And like I said, if anybody's interested in why this works, I wrote up a couple papers and put them on the enrichment page of your website, in case you need more mathematical proof as to why all this works. Everything I put on that page is, when I was sitting in your chair and people were telling me things, they would just say, it just works. And I would ask in my head, why? Why does it work? And I'd go home and I kind of work through it, like, oh, that's why it works, because you can work through it. But I wouldn't trouble you guys by doing that. But if you're interested, it's there. So all we've got to do is do that to our data, which means you have to have these three things. And as Hattie pointed out, we already have two of them given to us in the problem, yes? Those are given to you. That's 70, that's 3. This is now the 66 Skylar identified as you can't be any taller than 66. So we just do the conversion. I'll do it in red so it jumps out. So over here, we got to do 66 inches minus 70 inches over 3 inches. And notice everything's inches. When you divide off all the inches and inches, the units go away. And you lose the unit of measurement and you become unitless, which is the whole point. That standard normal curve doesn't have a unit. It's just pure. It's a pure mathematical construct, which is beautiful. We can get any curve onto it in that way. And this is where Kate's negative 4/3 came from. You're 4 inches down from average, but you have to scale that with the standard deviation to talk about how far down. If the standard deviation was only 1, 4 inches down is ridiculous. But since the standard deviation is 3, that's just outside of 1 standard deviation, which is not uber ridiculous, at least as far as position goes. So this little z-score right here is that negative 4/3. And so you realize that a standard normal curve with a z-score of negative 4/3 creates the same area as this normal distribution with a standard deviation of 3 and an average of 70, starting at 66. Cool? Fair enough? Now all we got to do is run the numbers, and we get our area that we need. It sounds like, okay, you just did it?
Yeah.
Okay, let's do it. Let's do it. I'm going to slide this up a smidge. Actually, I'll just turn it off. Okay, I'll slide this over. Make sure we can see it okay. Yeah, not bad. All right. Programs to normal. Forwards, left. Negative 4/3, yeah?
Yeah.
Yeah. Looks like our curve. 9%. So like 1 in 11 guys are going to fit comfortably under the shower head. Acceptable.
A lot of women will.
Wait, good, it's E3 actually.
Oh, okay.
The E3 is to figure out what percentage women will. Good, good, very good, very good. But my next question in E2, first of all, is everybody solid with how we got that 9%? Now, I asked this question in class yesterday, and I think it was a good question. Unfortunately, I think it confused the hell out of everybody. What would be a better method? Putting the shower head at 68 inches like this, or letting somebody walk in and giving them a quarter and saying, flip the coin. If it comes up heads, you'll fit. If it comes up tails, you won't. What's a better method for fitting people under shower heads?
That quarter?
The coin, definitely. Because under the coin, 50% fit. Half will fit. Right? And I think I must have asked it wrong yesterday, because if they were like, the shower head fits. But it only fits 9% of guys. The quarter will get 50% of them. And this is something, the reason I'm planting that seed in your mind, if you haven't started the project yet for Thursday, is very often a false positive or a false negative or a test result is compared to a coin flip for efficacy. How does it compare to a coin flip? In other words, how would you feel if a police officer pulled you over at a DUI checkpoint and instead of making you blow into a tube, took a quarter out of his pocket and flipped it and said, if it comes up heads, I'm going to arrest you? Well, probably pretty lame. You'd be pissed. But some tests are no better than that, as you'll see in your work. So, anyway, that would definitely be better than this, though. But, as Jenny pointed out, women would fit under here better. And that's why, if you look down, I give you the women's heights, 64 inches on average. Which clearly, more than half of women will fit. Because if the average for women is 64, that means the tallest they can be is 66, which means they bump over here now, which means this whole chunk of women are going to fit. So more than half. Still, I think too few, in my opinion. Not anywhere near like 95 or 96%, but more than guys anyway. And plus, like I said, you have fun when you turn it up and make a fountain. You can make a game out of it, bring Max in there.
66 inches is how is it comfortable?
That's my definition, because the thing was at 68. So I said at least 2 inches between your head and the top of the bottom.
It's like resting.
Well, exactly. So you're not just like right up against it.
I'm 2 inches taller than it.
There you go.
So-
There you go. Exactly. And that was my. And the thing is, it's hard to view this as an isolated event. Like I can walk into the shower, stand next to it, and I'm like, this is ridiculous. But that's why I go to statistics. I go, okay, is my gut feeling that something is wrong with this uniform, or is it just because I'm a slightly taller dude? And it turns out that it's not. My gut's probably right. We're only fitting 9 out of 100 people. Right? 1 in 11 people are guys are fitting comfortably. Probably 2 in 3 women are fitting comfortably-ish, somewhere in that neighborhood. Not a whole lot. I mean, 2 in 3 is better than 1 in 11, obviously. But it's still kind of low. Why would they do that?
Cheaper?
They're dumb.
Probably
Yeah, Skylar, that's harsh.
Probably an older-
I think it's cheaper. Or,
Probably an older building that was remodeled when people used to be shorter.
interesting, I've heard this before. Good, so we've had 3 reasons. Number 1, they're dumb, which is harsh as hell. Wow. Number 2, it's cheaper. Very often, Scott can check me on this one, I think that's going to be copper coming up and copper's not cheap. Copper's expensive. So if you can save, think about Ramada, they're a chain of hotels, yeah? They've got one of these pipes at least in every single room. So if you can lop off a foot of cost per room, per hotel-ish.
And commercial building codes are established typically around 1930s, when people were shorter.
Boom! Which ties into what Dawn said, yes. So if you're tied, and this Ramada's been there for say 100 years or 80 years, maybe the average height was not. It makes me a little bit skeptical, just because I'm me, to think that our average height has bopped up 3 inches in less than 100 years. I know we're fed better now than 80 years ago, but I don't doubt that we're taller. I just don't think we're that much taller than we were. And I could be wrong. My grandma Passanelli was tiny when we lost her, and so was my grandpa Passanelli.
Well, they were depressed because of the Great Depression.
Yes, and they were just hunched over. And they ate dirt, sand, so they shrunk. Yes, and so there's some very good reasons right there. If you base your average on a lower average, this percentage will be higher based on a lower average. So you can see that with the women's heights versus the men's heights. Assume that the guys' heights are centered at 70, the women's heights are centered at 64. It's a 6-inch difference. If that might be all it takes to account for the 6-inch difference, if there was truly a 6-inch difference in average heights, it could also be that the data weren't as complete in 1930 when the codes were established, so we had a skewed version of what average was. Very, very true. Maybe more wealthy people were measured because of affordable access to healthcare then, and they were somehow skewed compared to people that couldn't afford better healthcare back then. I don't know. I'm throwing things out now just to avoid either dumb explanation. Go ahead.
I'm guessing cost.
Cost is a very, very good one, I think. I think cost is a fair assumption because can they use PEX on those vertical runs or no?
Oh yeah.
They could. Well, that's the one way to get around it instead of using copper.
Yeah.
I don't know how much cheaper PEX is than copper though. Harrison, what do you got?
Wouldn't
Just thinking out
shower
loud.
time like save money too? Because if your showers, you're not comfortable in it, you're not going to take as long a
Oh,
shower.
that's brilliant.
So you're going to save in the long run.
That is make it uncomfortable.
Like not like it's like super uncomfortable, but you're not going to take as long of a shower, which will add up over time.
Or they were
No,
more
that's
concerned about their armpits.
that's the Office Space argument. Say that again,
They're
Scott.
more concerned
About the armpits than the head and the hair. No, that's the Office Space argument. How you can, if you take all the round-offs and add them all together, they add up to real money at the end. Real money on savings. That's clever. I hadn't thought about that. That's good.
Perhaps they're not fully retarded and they were.
Dumb.
Semi.
Dumb. Careful. Dumb.
I'm sorry. Fully stupid. Dumb.
Moronic. Idiotic.
Yeah, what's the
Imbecilic.
Yes.
One of those IQ scales. I
And they
forget.
were thinking about international averages, because I know on an international scale, I think 5'6" is the main.
Are we taller than some other countries?
We're way taller than
If
that.
you,
You want to go to China?
yeah, if you take the
I didn't know that.
hemisphere and
I didn't know that. Interesting. So a different set of standards. Again, stuff I don't think of. This is great. What do you got? What do you got, Kate?
Well, kind of off the comfortable.
Yeah.
That and the cookie cutter houses I've noticed, when the
Uh-huh.
pipe comes out of the wall, it kind of curves down a lot to make the shower head lower.
Like
than
at a
where the
weird
pipe is
angle?
actually- Yeah, and if they didn't do it at that funky angle, it would work better.
Maybe, and I don't remember. I should take a picture of it and put it in the homework too, because I can't remember if it came straight out or. Very often, when you look at the plumbing in some of these hotels, it's interesting. It's interesting, and you can tell it's been rehabbed a few times. And I can't remember if it did the bend or if it just stuck straight out and there was a shower head sticking on it. It's been a few years now.
And then my brother, this was a couple years ago, he was probably only about 6 foot at the time, maybe 6'1", but he spent the whole summer in Japan, And he said he was a good 6 inches taller than
Oh.
every single door. He
That
had to
makes
duct
perfect
tape it
sense.
into the doors.
Code is 80 inches, I believe, for doors. Is that right, Patrick? 80?
I don't remember.
I'm gonna throw a number out there, because that's 6 inches above 6 feet. So that's 6'6".
Yeah.
I'm looking back at those doors. That looks about 6'6", doesn't it?
But
Ish.
over in Japan, it's like.
Of course,
way
because you don't make
different.
code. You make code to an average. Essentially, you're gonna bump a certain percentage. You've ever walked into an elevator, for example? You walk into an elevator and it says maximum weight limit is 12 people or a certain amount of pounds. Well, they based that on a worst case scenario of 12 huge dudes getting in there, and they build the elevator strong enough to hold 12 huge dudes, on the assumption that you're not usually going to get 12 big guys in the elevator at the same time. You're often going to have a mix of genders, or you're going to have fewer than 12 people, or something like that. So it's all based on those averages and likelihoods that have you built it well enough or designed it well enough to satisfy. Now, a shower head is hardly something to get worried about because you're not going to die in a shower, hopefully. Of course, insurance companies have to account for that contingency too. People fall out in the shower. But an elevator is a much different story as far as building the code. So good ideas. It's very clever. I like it. Yes, please, Megan.
I think it's a hotel for midgets and you didn't read it.
I'm a pretty careful reader, though.
I'm just saying that.
Yeah, I think
My son was
shower
pretty
heads.
happy. My son was pretty happy. Speaking of that, thank you. I've noticed, and well, it's not done 243. I want to make sure it's not a systemic COC thing right now. A lot of my 105 students are having a hard time reading what I've sent out to them as far as like the out of class exams. Like at one point, I got an email today saying I can't figure out how to make a scatter plot from your project. And I look at the project, at the part on scatter plots, and there's a video link that links out to a YouTube video that I made that has 112,000 hits on it.
Really?
Yeah, and I'm thinking, did you see that? And he's like, no, I didn't see that at all. So I don't think this is a systemic problem. I think it's a 105 problem. I haven't heard anything like that from you guys, but just make sure you do read carefully. There's going to be a lot of texty kind of stuff on this last out of class, so make sure you're reading in, especially for things like the averages to standard deviations. Go in there and extract them from the problems. I give you little hints here and there, like go look at questions E1 and E3 and things like that. And you know, those are important because they'll kind of guide you if you need guidance. You can always email me, of course. But save yourself the agony of having to wait around for a response and just make sure you really... I think it's more of a 105 problem because I've gotten dozens of emails from them this term on, you know, you didn't teach us how to do this, and I'm looking at the video and I'm like, well, there I am doing that. So, just thank you, Megan, for bringing that up. It never hurts to hear it again. All right, and I do read, thank you. So Scott, that makes sense. Good. And then the only thing that makes this a slightly different kind of problem is the fact that you have to deal with the 2 inches. That's the only thing. The 2 inches is the only thing. So basically, all you got to do is kind of make your mind, okay, how tall can the guy be or the girl be? 66. Can't exceed 66. And that's where the 2 comes from. So now, did you catch how we took the 2 inches off in the beginning here? That was the first thing we did. It was 68 inches. We knocked it down to 66 and put that on the curve. So if you made this a forwards problem, the first thing you did was subtract 2 inches. Later on, I make you do a backwards problem, which means the last thing you'll have to do is add 2 inches back on. Because I asked you later, at which height should the shower head be placed so that a certain percentage of people will fit under it comfortably. So you're going to have to find that percentage, find the z-score, it's going to be somewhere over here, figure out what the z-score is, figure out what number of inches that corresponds to, but that tells you the highest guy, that's the 95th percentile, his cutoff height. You then have to place the shower head 2 inches above that height, yeah? In order to be comfortable by my definition. Yeah, Kate?
I was just going to clarify, in that little paragraph where we're saying,
Yeah.
it said the average height of the guy was 70 inches, right?
It did.
Okay.
From the, yeah, and I have to supply you with those. That's why what Megan said is so crucial. I have to supply you with those pieces of information. I've seen goofy, mathy kinds of problems like this where I don't give you like the standard deviation and make you solve for it, and I just hate those problems. They're too mathy. I have to supply those. Yeah, they become a math problem, not a stat problem. I have to give you those numbers and then let you analyze around using those. Thank you. Yes. And that's as Hattie pointed out, that's something to look for, to know what kind of problem you're dealing with. If you're given the mean and the sigma, you're dealing with a normal problem in this section of the course. Cool? What else in there gave you grief? That was just the 2 inches was the goofiness. Good. So the 2 inches will help you. This problem will help you do that. I think it's a United Airlines, or I forget which airline I used. I forget. On the out-of-class exam, we talked about designing seats, and you need wiggle room to be comfortable in a seat. And I think I invented it. You have to have a ½ inch on either side of your hips to be comfortable. I'm not sure if that's an industry term. I just decided. Well, by airplane standards, it's pretty luxurious. Crammed into a seat.
No, but
Well, it's okay. I'm not missing a whole lot. I mean, it's fun. There's a great Louis C.K. skit about that. But anyway, I just defined you can't have the seat exactly match the average hips of somebody, because you're going to then piss off at least half the population, because you're going to cram an average-sized person directly in the seat. They're going to fit exactly perfectly, which means not comfortably at all, because they can't go side to side at all. And then anybody above that won't fit at all. So you're going to get less than half the population. So you have to put some kind of a wiggle. And this goes for not just airline seats. If you ever go to the hardware store, or if you're, better yet, if you're at your house trying to find a nut that matches a bolt, you know, like a shelf fell off the wall, you're like, I can fix that. You go out to your little drawer of nuts and you pull them out, and you're trying a nut, you're trying a nut, you're trying a nut. A nut doesn't fit a bolt perfectly. There's a little tolerance around it. It wiggles a little bit as you're putting it on. That tolerance is a sigma. It's a standard deviation. It's amazingly tight on those parts, because if it's too wide, the bolt will just pull straight out. But pretty much everything has those little things called tolerances, whether it's an airline seat, whether it's a shower head, whether it's a bolt on a nut combined together. You have to have some kind of a tolerance. You can't make them fit exactly or they won't fit. I encourage you to try this sometime. If you have to cut, say, an 18-inch piece of wood to fit an 18-inch hole, don't cut it to 18 inches, because it won't fit. Because you can't get it into that exact 18-inch hole. You have to have a little tiny bit of, I think it's called a kerf with wood, a little tiny bit of give to get it to pop in. And depending on the skill of the people using the tool, or the tool you're using, you can make it a very, very small tolerance. But it can't fit perfectly. There has to be a little bit of a give in order to have it actually either fit well or get it into position to fit well. So, sorry, getting sidetracked a little bit there. Anything else in here? Good theories on the why the shower head's so. I love the uncomfortable theory. That makes me happy. It makes me happy just because it makes sense. It's like a psychological reason. Let's save money on water bills by keeping the shower less. I like it. It's a less nefarious version of the Ford Pinto from the 70s, if you remember. I don't remember, you guys are so young, but Ford Pinto, I believe it was the Pinto, had a problem with exploding gas tanks. Yeah. And the movie Fight Club actually had a joking reference to this. If you remember the one scene in Fight Club where Eddie Norton is sitting next to, what's his name? Brad Pitt, thank you, on the airplane. And he's describing what he does. Brad Pitt's describing what he does for a living, and he works on an insurance adjuster. And he says, what do you do? And he talks about how, you know, they take a catastrophic event, and they say, well, how much is it going to cost? And what's the chance of it happening? So how often does it happen? How much does it cost? Multiply all this stuff together. If the end result dollar amount is less than the cost of a recall, then don't do the recall. Which is essentially what Ford did with the Pinto. They just decided to start paying out the claims on these exploding gas tanks rather than fixing the problem. Which, as you can imagine, once that hit the airwaves, was not the greatest PR campaign for Ford, and they had to retract that. And it wouldn't make it even a half of a day in this day and age with internet communication as quickly as it is. But that's the idea. That's the idea. You use these likelihoods to kind of weight pluses and minuses. Now that shouldn't even be a plus or a minus. That should be a fix. Exploding gas tanks, for goodness
It was like a
sake.
big explosion too.
Well, it's a gas tank exploding. It's 15 gallons of gasoline.
Well, I mean the way it was sat.
Yeah. Anything exploding in a car is terrifying. Yeah, think about it. But anyway, it's just interesting how this leaks into, how this kind of stuff leaks into your daily lives without necessarily you realizing it. So, cool? Good. All right, we're going to stop again. Yeah, we can get this started before